Okay, I give you the brief solution. It's now we use the formula. Z prime is equal. Z prime is equal. Z prime is equal. Now, from the equal, you can see the function f(x) f(1), uf equal f(t) is equal t squared sin t. Okay? Now, apply the formula. What we have? Apply the formula. What we have? We have the z prime f is equal the integral prime. Okay, equal f af times f prime minus f u prime. We replace af equal 1, uf equal x, ft equal t squared sin t. You write down before you continue. Okay, we replace the s by 1, ux by f. At f(1), we have the f prime equal 0. U equal x, we have the e prime f equal 1. Okay, we can replace that. when we replace x at 1, u equal x, okay, we obtain the final result. Z prime x is equal minus x squared times psi x. Okay, if we need to find the derivative function, and the two limits depend on x. Now, let me give you another example. We need to compute the limit. You can see the numerator here, integral. Integral depends on x. And two limits depend on x. Okay, now, first of all, I need to amplify the derivative of numerator with respect to x. Nào, đầu tiên các bạn thử tìm cho mình cái đạo hàm của cái hàm ở trên tờ phần từng số theo x nào. In this example, we use second parametric term and L orbital to find the limit. Okay, I think very easy to see the limit here. It belongs to form 0 over 0. Okay, 0 over 0 form. So we can apply the orbital for this limit. Of course, if we want to apply the orbital, we need to compute the derivative of numerator and denominator. Now, find the derivative of numerator and denominator before you compute the limit. you need to find the derivative numerator. Okay. I think you can see the derivative here is equal sin x squared times sin x times cosine x. Okay. Now we start to solve. We start to solve the example. In this example, we use orbital rule. And substitute rule for equivalent in infinitesimal. Substitute rule tức là quy tắc thay thế tương đương. Được chưa nhỉ? Substitution rule là quy tắc thay thế cho các vô cùng bé tương đương. Okay? In this example, we use orbital rule, the substitution rule for equivalent infinitesimal, and the sum equivalent infinitesimal you know. Now, you can see when x tends to 0, we have a sin x approximate, sin x equivalent x. Okay? Sin x tends to 0. Of course, we have the sin x equivalent to sin x. Okay? We have the formula here. Now, we continue. In the example, we want to use orbital rule. If we want to use orbital rule, we need to check the limit which form. Okay? You can see when x tends to 0, we have the numerator tends to 0, denominator tends to 0. Okay? So the limit equal here it belongs to 0 over 0 form. Of course, we can apply the orbital rule to this situation. Okay, this is here. We can express the limit here by derivative. Okay, I think we need to find the derivative of integral. We can use the second fundamental theorem. Okay, second fundamental theorem. We can find numerator is equal sin x squared times sin x times cosine x over 4x cubed. Okay? You can see when x tends to 0, we have a cosine x tends to 1. Okay? So we can use this cosine x. Okay? We have the limit. Okay? To continue, we use substitution rule for equivalent infinitesimal. Okay? We can replace sin x by x. Okay? Sin x by x. Okay? The limit here is become the limit x cubed over 4x cubed. Okay? We can reduce. It equals the limit 1 over 4. Final zero, 1 over 4. Okay? We need to find the limit. The method is based on orbital rule and second fundamental theorem. Okay? I think you can write down this process. Okay, we need to recommend two fundamental terms. Okay, we continue to listen to the sum method to compute definite integral. Okay, you need to write down. Now, to continue, we listen to the sum method for compute definite integral. It is here we recommend the four methods. The first is listen to the subdivision rule. The second, integration by part. The third is listen to the recursion formula. Recursion is that means shearhole. Okay? The finally is listen to the induction. Cuối buổi tôi gửi lại các bạn các slide của bài giảng còn lại nhé. Các bạn có thể tìm hiểu trước. And the new variable u depends on x, u a function of x. Listen to the first term. This may be we can integrate the function f and the function of t. Okay? We have the two change variables related to substitution rule. The first term is the u, the function of x. The function of x. We can express the definite integral with respect to x by definite integral with respect to u. Okay? This is here x varying from the a to b. We have the new variable u varying from the ZA to ZB. Similarly, if we change variable, we take substitution rule. X equal at t. We can express integral with respect to x by integral with respect to t. Upon the function z and function x satisfy some condition. Okay, let me give you an example. Evaluate the integral from 0 to 1 exponent n cosine exponent here. Okay, it's an example. We is the first term. We is the first term. We take the new variable. U is equal exponent. U is equal exponent. Okay, we need to write out two terms. Okay, now we show the example. We show the example. In the example, we take substitution. U equal exponent. For simplicity, we let the I is equal. I is equal. Now, take substitution. U equal exponent. What we have? What we have? Okay. We have difference of u is equal exponent here. Integrand, the function of x, we can express by the function of u. Okay, integrand times dx is equal cosine u du. Okay, to continue, you can see when x varies from 0 to 1, equivalent to e varies from the 1 to e. Okay, now we want to express the integral with respect to x here by the integral with respect to u. Okay, we can express the function. Express the integral by the integral with respect to u. Okay, I think the integral here is very to estimate. Okay, we can use the Newton limit. We can use the Newton limit in this situation to compute definite integral. Cosine u equaling from u equal 1, u equal e. Okay. you a function cosine, okay, over here cosine here. We replace the e equal e equal 1. Sine e minus sine 1. Okay, we need to compute, evaluate the definite integral. From lowering to y. Then we can find the definite integral from the a to b UdV is equal uv. Okay, radical value from the a to b minus integral from the a to b du. See, the first way, we can view integration by parts directly. In this formula, we integrate the u and v and the integral with respect to x. Okay, we regulate x value from the a to b. Okay, we can estimate. We can estimate definite integral here directly. The first way, application 1. The second way we can apply the integration by parts for definite indefinite integral. After that, we can use the Newton leveling, to estimate the definite integral. Second way. The first, you can apply integration by parts for indefinite integral. Then we use Newton leveling formula to evaluate the integral. That means the first, you can find the antiderivative of function u v prime. The second, we use the Newton leveling to estimate. Okay, let me give you an example. Evaluate the integral from the 1 to e natural logarithm x dx. start with the first way. We use integration by parts directly. Now let's see the solution. Let's see the solution. Let u is equal natural log x b prime equal 1. Okay, we can imply that u prime is equal 1 over x, b equal x. We apply integration by parts directly. We have integral from the 1 to e natural log x here is equal. We replace the u and b. The value here is equal x natural log x varies from the 1 to e minus integral from the 1 to e. We replace the b is equal x, e prime equal 1 over x. Okay, we can derive. The last factor is equal integral from the 1 to e, 1 dx. Okay, I think very easy to estimate the final result is equal 1. Okay, the first way applies integration by parts directly. The second way, I think we need to find antiderivative of function natural log x. To continue, we use Newton-Leibniz formula to estimate definite integral. Okay, so we need to do first solution. Okay, now continue. The second solution, we need to use the antiderivative to evaluate definite integral. The solution 2. The solution 2, you can see the first, you need to find the antiderivative of function natural log x. Okay? We find the antiderivative here is based on integration by part for indefinite integral. Okay? You can find the antiderivative of function natural log x is equal. It equals x natural log x minus x plus c. Okay? To continue, we use Newton-Leibniz formula. Okay, here we use the antiderivative to find definite integral. Then the same divide equal 1. Okay? Now, to continue into the first, okay, method 3. The method 3 is into the recursion formula. Recursion formula. Conclusion. Okay, recursion formula means that we can compute the value I sub k plus 1 in the previous value of the sequence I sub n. Is that mean we can find I sub n plus 1 is based on previous term of sequence. I sub n plus 1 is equal f I0, I1, etc. In. Okay? Does that mean we can find the in plus 1 is based on previous elements in sequence. Okay? To illustrate for recursion formula, I give you an example. Establish recursion formula for integral I sub n is equal integral from the x power n exponent x dx, where n belongs to natural number set. Natural number set. In this example, we use integration by parts to establish recursion formula. The idea for this example.